The Laser Interferometer Gravitational Wave Observatory, or LIGO, is a gravitational wave detector. It detects ripples through space itself caused by the catastrophic merger of two black holes. So far, LIGO has detected a handful of these black hole mergers in the past 4 years or so, the biggest of which was two black holes, one that was 85 times the mass of the Sun and the other that was 66 times the mass of the Sun. It does this by detecting the change in distance recorded by lasers firing at mirrors in an L shape. So if a wave passes through, it squashes and stretches space itself, and the distance you measure between those two mirrors change. The bigger the black holes in the merger, the bigger the gravitational wave, and therefore the bigger the change in distance that you detect. So why hasn't LIGO detected the merger of two supermassive black holes that are 1 million to 1 billion times the mass of the Sun that we find in the centers of galaxies? Galaxies are merging all across the universe. We see them everywhere, along with their supermassive black holes in the middle. So what's up with LIGO? Why can't it detect supermassive black hole mergers? All right, first and foremost, gravitational waves, i.e. these ripples of energy through space itself, by the time they reach us here on Earth, are tiny. Yes, very close to this cataclysmic black hole merger, they will be absolutely huge, but they dissipate as they spread further and further through space, in the same way that, you know, if you yell really loudly at the top of your lungs at a certain distance, you won't be able to hear it anymore because the energy in that sound wave of your yell has dissipated. So when I say they're tiny when they reach us, I mean it. The squashing and stretching only causes a change in the distance between those two mirrors of less than the diameter of a proton. It's around about 0.000000000000001 meters. That's 15 zeros after the decimal point and then a 1 meters. So if we think about how LIGO might work, how it could measure a change in distance between this laser firing and a mirror, right? Well, we can get distance if we know how long it takes for the laser to be fired, bounce off the mirror, and come back again. Because we know the speed of light in the laser. It's the speed of light. And then we can just get it distance from the time it takes times by the speed. Distance equals speed times time. But that's not how it does it, because you couldn't make that measurement of distance down to 16 decimal places like you would need to do it. Our equipment, even our clocks, are not that accurate to be able to do that. So instead, actually uses a really cool quirk of physics that's actually used in noise-cancelling headphones as well, and it's called interference. Light and sound are all waves, right? So they have a wavelength between two peaks and an amplitude. And if you have two waves, they can be in sync. So the peaks line up, which means if you add those two waves together, you get something twice the amplitude. If it was a sound, you'd get something twice as loud. Or two waves can be out of sync. So the peak of one lines up with the trough of another, and then they completely cancel out if you add them together. This is what noise-cancelling headphones do. They record all the external noise, say like the roar of an airplane engine or a hairdryer or something like that. They record that sound, invert the wave, and then play that sound wave into your ear at the same time so that the two cancel out and you don't hear anything. So LIGO's L-shaped mirror layout is set up so that the laser comes in and is split down the two different arms that make up the L shape. And they both travel up, bounce off a mirror, and then are recombined again. They set it up so that one half of the laser that's split travels a half a wavelength more than the other side, so that they're completely and perfectly out of sync with each other, so that when they add them together, they cancel out, and the detector that's recording, if it's detecting any of that laser light, says, nope, there's no light coming in because those two things have cancelled out. So all being normal, the detector will always record no light. But if a gravitational wave passes through, then the distance that the laser light travels on either arm changes by the squashing and stretching of space, so the two waves are no longer perfectly out of sync when they're added together again, and the detector records a tiny bit of light coming through. It's a really clever sort of physics hack way of measuring those incredibly tiny distances of 16 decimal places. But for this to work, the distance the laser light travels down those two L-shaped arms has to be around about the wavelength of the gravitational wave you're trying to detect. And the wavelength given off depends on how massive or energetic the object is that's generating them. So less massive black holes will emit shorter wavelengths, whereas huge supermassive black holes will detect much longer wavelengths. Now, LIGO's L-shaped arms are 4 kilometers long, which is an incredible feat of engineering, especially when you remember that they're also buried underground. In terms of gravitational wave wavelengths, it's on the piddly side. It means that LIGO will only ever be able to detect the gravitational waves from mergers of objects that are around about, the mass of stars. So about 1 times the mass of the sun for neutron stars, all the way up to, say, 100 times the mass of the sun black holes. It will never be able to, it physically cannot detect the gravitational waves from the mergers of 2 supermassive black holes. But plans are afoot at the European Space Agency for a space-based gravitational wave detector. A mission called LISA, the Laser Interferometer Space Antenna. We use the same method as LIGO, but with 3 spacecraft in a triangle separated by 2.5 million kilometers. And they'll all trail the Earth in its orbit around the sun, making this sort of amazing triangular dance. It's a very ambitious project, and there's lots to do and lots of problems to solve before its planned launch in 2034. But with it, might just be able to detect ripples from one of the universe's most epic and cataclysmic collisions between 2 supermassive black holes. Before we get to the bloopers, I just want to say a big thank you to this week's video sponsor, Brilliant. Brilliant is a website and an app with a huge range of courses on all different topics in science and maths that get you to learn by doing. It's never too late to start learning something new, and I think Brilliant is a great place to do just that, especially because they've upped the interactivity on their courses recently to a whole new level. I especially love their course on scientific thinking. It introduces you to different physics concepts through these interactive puzzles. It's so good for gaining physical insight into things that would usually need endless equations to describe, right? But instead, you can visualize what's going on with these little interactive widgets. So if you'd like to try out Brilliant for free and get 20% off a yearly subscription, head to brilliant.org/Dr. Becky. The link is in the video description down below. Thank you so much to Brilliant for sponsoring this video. And now, roll those bloopers. So if we think about how LIGO might work, LIGO, my LIGO, legless, Legolas. Now LIGO's LIGO's L-shaped arms are only 4 kilometers. Ugh, come on, Becky. We're in Earth mode now, not astrophysics mode. It's on the piddly side. It means that LIGO will only be able to. Oh, I love it when these gravitational waves ripple like that. The way they move through the detector got me rippling like that.